Okay, so in the previous video, we talked about work done by variable forces, but now we're going to look at a specific force that is varying often. Okay, so now if a spring obeys what we call Hooke's law, right, which is that F equals kx, right, so F equals kx, or actually negative kx, then we can use the integral to find the work done by the spring and its displacement changes from xi to xf. Okay, so in fact, that should go right here. So recall that the force of a Hookean spring is given by the equation F equals negative kx. Now remember, the negative sign, okay, indicates that the force and displacement are in opposite directions, right? Just remember, Hooke's law, or this, the spring force is a restoring force. So it wants to bring it back to its initial equilibrium position, okay? And so here's just the quick example where it says derive an expression for the work done by a Hookean spring that is stretched from xi to xf. And so the work done by the spring is going to be the integral from xi to xf, right, of our function, which is going to be negative kx, right? So negative kx dx. And so if we do just a little bit of cleaning up, we can factor out that, or pull out that k, because that's just the constant. And so we're doing the integral of x dx. Remember, when you do the integral of a line, it becomes a parabola. And so it's going to be negative k times 1/2 x squared evaluated from xi to xf. And so all we got to do now is plug in our xf and xi. And so we end up with the work done by a spring is equal to negative 1/2 k xf squared minus xi squared. Okay, and so if you look at formula sheets, this is the equation given for two things. One, the work done by a spring, but this is also the potential energy stored in the spring. Okay, and we'll get a potential energy in a couple of videos, right? All right, so here is. So if the spring is stretched to x, and pushes or pulls on an object, right, to the spring's equilibrium, then the work done by the spring is just simply 1/2 kx squared, right? The equilibrium thing about it is when x equals 0. All right, so here's just a quick example. The pin cube machine was an ill-fated predecessor of the pinball machine. A 100-gram cube is launched by pulling a spring back 12 centimeters and releasing it. The spring constant is 65 newtons per meter. What is the cube's launch speed as it leaves the spring, assuming the surface is frictionless? Okay, so we're going to do the work done by the spring and stretching it to that 12 centimeters is simply 1/2 kx squared. So it's going to be 1/2 times 65 times 0.12 squared. Make sure that you do convert this to meters. And so that'll be 0.468 joules. And then we go back to our, right, delta K equals W. And so the speed of it coming off the mechanism would be 2 times the work divided by the mass. Again, convert this mass, right? So we need to make sure we're converting to meters and kilograms. So it's going to be the square root of 2 times 0.468, which was our work done, divided by 0.100, and we're going to get a speed of 3.05 meters per second. Okay, and I'll tell you that's the reason why it was ill-fated, right? Because it was a cube, right? And so it's not going to do much and be much fun in the long run. Okay, so from now we're going to look at we're going to start focusing some efforts on potential energy, forces, conservation energy, and then ultimately end up with power.